Children, in this video, we will be discussing first of all the merits of Bohr's model of atom. As you know, we have already discussed, Bohr was able to give expression for energy of different orbits, and he gave expression like this: minus 2.18 into 10 to the power minus 18 by n square joules per atom. Energy of, say, nth orbit, he gave like this, and Bohr's model of atom, there is a nucleus, the center, and we have orbits, different orbits. This orbit is, say, k, where n equal to 1. This orbit is L, where n equal to 2. This orbit is M, where n equal to 3, and so on. This orbit is, say, n, where n values is 4, and so on. There are many orbits, so this is your Bohr's model, and the energy of a particular orbit is given by this expression. And in case of your a general expression, it is minus 2.18 into 10 to the power minus 18 into z square by n square, where z stands for the atomic number of one electron species. Bohr's model of atom is applicable for one electron species. Like z value for helium, it is 2, z value for lithium, it is 3, and so on. And another merit of Bohr's model of atom is he was also able to give expression for radius of different orbits, and the expression was like this: 0.529 into n square by z, this much angstrom. It was the expression for radius. If you put n value 1, you get the radius of the first orbit, n value 2, you get the radius of the second orbit, n value 3, radius of third orbit, and so on. Another very important thing is that Bohr's model of atom could explain the spectral lines. Now, let me remind you, in case of hydrogen atom, we get emission spectrum. We get emission spectrum like this. Emission spectrum like this. So this is increasing wavelength, and this series of lines is called Lyman series. This is called Balmer series. This is called Paschen series. This is called Brackett series, and this is Fund series. So Bohr's theory was able to explain these spectral lines. Now we'll discuss it, how we can explain the spectral lines, in terms of Bohr's model of atom. Okay, now children, you know that Bohr in his theory has said that electron, when it is revolving in its orbit, it neither loses energy nor gains energy. But what can happen is that if we supply energy to an atom from outside, then electron gets excited and it can go to higher energy level. It can go to higher energy level. For example, suppose we have here hydrogen atom, and hydrogen atom has one electron, and suppose we have hydrogen atom in the ground state. Ground state means minimum energy state. So electron of hydrogen atom will be here in the first orbit. Now, if we supply energy to hydrogen atom from outside, this electron will go to higher energy level. This electron will jump to higher energy level. Suppose it is K, it is L, if it is M, electron can go to L. Depending upon the energy, electron can even go to M. Electron can go to N, and so on. So, suppose we have this atom only in the excited state. This atom in the excited state, previously the electron was here. Now suppose the electron has jumped and it has gone to here. So this is hydrogen atom in the excited state. So when we supplied energy and the electron has jumped to excited state. Now, electron will not remain here in the excited state for long. After some time, it will again come back to its original ground state. It will come back. So, obviously, when the electron will come back to its original state, it will emit energy. How much energy will be emitted? Okay, how much energy will be emitted? When electron comes back to its initial ground state, okay, energy is going to be emitted, and energy emitted will be, say, E2 minus E1. Suppose energy of this orbit is E2, energy of this orbit is, say, E1. So when electron comes from here to here, it is going to emit energy. Emitted energy will be E2 minus E1. Suppose if it is delta E, then according to Planck's quantum theory, this delta E is going to be h nu. And what will happen is that there will be radiation emitted. There will be radiation emitted of frequency nu. There will be radiation emitted of wavelength lambda, and this radiation will correspond, will account for a line, one line. So this radiation will cause a line in the hydrogen spectrum. So in this way we can account for spectral line. Now question arises, why say so many lines? Why so many lines? The reason is that we can explain this way, that first of all, when we have taken hydrogen gas in the discharge state, hydrogen initially is in molecular form, and when we pass discharge, then the molecules breaks down into atom, and then in the atom, what happens? Electron gets excited and goes to higher energy level. Now, since there are many hydrogen atoms, what happens is that, suppose in some hydrogen atom, it will get excited to, say, second quantum level. In some other hydrogen atom, say, it gets excited to fourth quantum level. In some other hydrogen atom, say, it gets excited to, say, 10th quantum level. So the excitation can take place to different level. That means we will get different value of delta E. Suppose delta E will get delta E dash, delta E double dash, delta E triple dash, delta E. So different energy will be involved, and if different energy is involved, so obviously it will be the H nu like this. Here it will be H nu like this. Here it will be H nu. Here it will be H nu. So you see, different frequency will be involved, and if different frequency is there, then each of these different frequency, as you can understand, will account for a different line in the hydrogen spectrum. One more thing that also we should take into account is that when an electron, say, has been excited to, say, the fourth level, electron has been excited to fourth quantum level. Now it will come back to the first quantum level again, and energy will be emitted, that you know, that we have just heard. But the thing is that there are different ways it will come back here. It can come from here to here, so some energy will be released. It can come from here to here, some different energy will be released. Then it can come from here to here. So you see, 3 transitions are involved. So 3 frequency will be involved, 3 lines will be involved. On the other hand, say if it comes directly from here to here first, and then say here to here, then for this one frequency will be involved, for this another frequency will be involved. So in this way, I think you are trying to understand that when electron gets excited to a higher quantum level, it comes back, it can come back in different ways, and each way will correspond to a line in the hydrogen spectrum, or in case of any element. So it is in this way Bohr had explained, or Bohr's model of atom could explain the spectrum, hydrogen spectrum. But in spite of so many merits, there are also drawbacks. There are also demerits of Bohr's model of atom that we should be discussing now. So demerits of Bohr's model of atom. We know that radiation has dual nature, that we have discussed, and this concept was extended to matter. This concept was extended to particle, and it was seen that matter or particle also has dual nature. matter can behave as a particle. Matter can also behave as a wave. And there are experiments, which has confirmed this. Matter can behave as particle as well as wave. Now, Bohr's model of atom, in Bohr's model of atom, Bohr had considered electron, only as particle. He did not consider electron as wave. So this is one serious drawback. Now, due to this dual nature, there arises a modern concept, that is, say, Heisenberg's uncertainty principle. Heisenberg uncertainty principle, and according to Heisenberg uncertainty principle, it says that it is impossible to exactly determine the position and the momentum of microscopic particle with certainty. We cannot determine simultaneously the exact position of microscopic particle and momentum of microscopic particle. So this is what is known as Heisenberg uncertainty principle, and it is because of dual nature of matter. So mathematically, Heisenberg uncertainty principle will be like this: delta x. Suppose delta x is the uncertainty in position of a microscopic particle, and suppose delta p is the uncertainty in momentum of the microscopic particle. And Heisenberg uncertainty principle says that the product of these two uncertainties is going to be greater or equal to h by 4 pi, where h is the Planck's constant. Where h is the Planck constant. Now, suppose the particles that we come across, say macroscopic particles. Suppose when say a cricket ball is in motion, or say a vehicle is in motion, or for that matter any other thing, macroscopic particle, the particle that we come across are in motion. Then with the help of classical physics, using this relation, v is equal to u plus at, or s is equal to ut plus half at square, or d square is equal to u square minus 2as. With the help of this equation, we can determine the position and momentum of macroscopic particles. But with respect to microscopic particles, that cannot be done. So for microscopic particles, we have Heisenberg's uncertainty principle, and this is the mathematical statement of Heisenberg uncertainty principle. And Bohr had given the idea of well-defined orbits. Bohr had given the idea of well-defined orbits. It means, as if according to Bohr, we can determine the position of electron. So that is not correct. That is not correct. Another serious drawback or demerits of Bohr's model of atom is Bohr's model of atom, Bohr's atom was non-directional in nature, non-directional in nature, and Bohr's model of atom could not explain the formation of bonds in molecule in a certain direction that Bohr could not explain. For example, you must be knowing that carbon dioxide is linear, having linear geometry. Boron trifluoride has trigonal planar geometry. All these things we will be studying in chemical bonding chapter. The geometry of molecules could not be explained by Bohr's model of atom, because according to Bohr, an atom is having no direction. And another major drawback is when we are getting these spectral lines, when we are passing the radiation that is emitted from atom through a prism, and then we are making it fall on a film or photographic plate, we get the spectral lines. Okay, but if these radiations, if it is subjected to magnetic field, then what it is found is that suppose this is a spectral line that we get. Now, in presence of magnetic field, what is found is that this spectral line, in presence of magnetic field, will split into more closely spaced lines. So this line, in presence of magnetic field, will become like this. Now, Bohr could not explain this splitting up of spectral lines in presence of magnetic field. The splitting up of spectral lines in presence of magnetic field, is called Zeeman effect. Zeeman effect. Now, Bohr had no answer to Zeeman effect. In the same way, there is a similar effect, is that when these radiations are subjected to electric field, then also it is seen that the spectral line splits into closely spaced more lines, and splitting of spectral lines in the presence of electric field is called Stark effect. It's called Stark effect. So children, what we have seen here is that Bohr's model of atom has got merits also, and it is also not free from defects. So we will discuss later on your another model of atom, that is quantum mechanical model of atom, that we will be doing in another video. But before that, we should be trying to get an expression for wavelength for matter wave. So that is what, suppose we know from Planck's quantum theory of radiation, we know E is equal to h nu. The energy of a quantum, is given by E is equal to h nu, and we can write h c by lambda. And according to Einstein's theory of relativity, we also can write E is equal to mc square, where E is the mass of photon particle and c is the velocity of light. Photon is a special type of quantum. In case of light, the quantum is called photon. So if we equate this, what we are getting is 8c by lambda is equal to mc squared. So if I take the reciprocal, we will get lambda by 8c is equal to 1 by mc squared. So lambda will be equal to 8c by mc squared. So if I cancel out c and c, we are getting is 8 by mc. So this is the relation that you should remember. And suppose this relation we had got for photon particle for light. Now it was said that this relation can be extended to material particle also, to macroscopic particle also. So if we write this one for macroscopic particle, we write like this: lambda is equal to 8 by mv. And for material particles, this equation is called Lewis, or this equation is called de Broglie's relation. De Broglie's relation. This is called de Broglie's wavelength. And what is the significance of this relation? Is that suppose we have a particle. Suppose this particle is having mass m, and suppose this particle is moving, say, with velocity v. So a particle of mass m moving with velocity v, it says that it will be associated with a wave. It will be associated with a wave, and the wavelength of that wave, of that matter wave, will be given by this relation. Lambda is equal to h by mv, where h is the Planck constant, where m is the mass of electron, mass of that particle, and v is the velocity. And you can make it out from this relation. This wavelength, this wavelength or this concept of wave will be more significant for microscopic particle, because microscopic particle m value will be very small. If m value is very small, lambda value will be high. So microscopic particle will have wave character, significant wave character. But as far as macroscopic particle is concerned, m value will be big, lambda value will be then small. Lambda value small means less wave character. So this relation, this de Broglie's relation, is more significant for microscopic particle than for macroscopic particle. We'll be doing numericals on this later on. So children, I think we should do this much only here. In my next video, I will be discussing about quantum mechanical model of atom. Till then, bye bye and